Hi, this is Terry Kozma from the Penn State NACK Center, and today I'd like to go over some characterization techniques for materials and nanotechnology. We're going to review EDS, XPS, SIMS, and FTIR. So this is the outline that we're going to go over today, and here's the topics. Energy Dispersive Spectroscopy, EDS, is what we're going to start with today. So EDS, it's an energy dispersive X-ray spectroscopy, is an analytical capability that can be used in conjunction with the TEM, SEM techniques. And why we can use this in conjunction with those techniques, we actually utilize the electron beam to initiate our signal. This technique is also sometimes referred to as energy dispersive X-ray analysis, which is EDXA. Basically, electrons are shot at a sample, and a unique electron-electron interaction produces a characteristic X-ray. So here's a block diagram of what we're going to overview today. And as I pointed out before, here's this system here is our E-beam gun. And naturally, we have an E-beam gun. E-beam gun is a part of the SEM, FESEM, or TEM. So what we can do is we can, in those types of tools or a separate tool, we can place a proportional analyzer. So what we have here is the electrons stream out of the electron beam. They hit into the sample. And then from the sample, what we do is we would collect the signal and then measure our X-rays at that point. So basically what this test is we have electrons, and from interaction with the sample, we emit X-rays. So energy dispersive spectroscopy, the SEM gun emitted electrons collide with the electron within the sample, causing some of them to be knocked out of their orbits. These electron shell positions are filled by high energy electrons which emit X-rays in the process. So we can see if we would kick this blue electron out per se, what will happen is this red one will relax into its position, and then we're going to emit this characteristic X-ray, and that's what's used for the analysis. This test, like all tests, has a niche where it's appropriate. This is sensitive for low Z elements, boron through uranium, and it's not appropriate for high Z elements. Elemental detection is typically 0.1 to 1 atomic weight percentage. That's really not very high, so this is a kind of a quick test. If you wanted something that had a lot of resolution, you would go to a test as SIMS, as we're going to review later on in the note packet. Windows, which are actually, like a glass window in front of the detector, can absorb low energy X-rays, so EDS detectors cannot detect hydrogen, helium, and lithium. And a lot of tests have troubles with the smaller, based on their physics, they have difficulty detecting those elements. So here's some pictures we took at Penn State here on our Zeiss Gemini tool, and what we can see on the left is the secondary electrons, and then we can look at the backscattered ones, and what we can do is actually color code those so that things stand out. So you can see on the right there's more, you can see the gold on the tip of that nanowire a lot easier. So these are nanowires that we grew here at Penn State, so they're silicon nanowires. We initiate them with a gold catalyst and grow them from there. This is another look at that same picture. This is elemental mapping, and what you can do in the software, you can assign like silicon, which would be shown in the green right here. You can look at the silicon and assign that a color. So we assigned that green, and then we picked red to contrast that as the gold tip. So anytime you look at the picture, you can get this color encoding by actually assigning the chemistry a unique color, so it lets things stand out appropriately. And this is another characteristic look at what we were studying here. So this shows the clean silicon nanowires. This is a well-prepared sample, and we can go through and we look at what we see on the sample. So what it shows you is actually the different types of chemistry, like carbon and oxygen and gold and silicon, and then the amount is shown on the left-hand side on the y-axis. These are contaminated silicon nanowires, so we can see that this system here, the nanowires are starting to grow, And I think what that residual stuff on there is photoresist. So we can take a closer look at that on the next slide, or a step back and show that same stain, which would be probably, I think it's residual photoresist on there. And when we take a look at that on the sample, we can actually see that there's sodium in there, more oxygen, etc. So this is a look at these two different types of silicon nanowires, one which wasn't contaminated with residual photoresist, and the other one that has residual photoresist and a bunch of garbage on there. And you can also in the software go to some quantitative results and look at them as a scale. So we can look at the percentage weight, what was occurring on that system. So EDS, again, the impact of electron beams on the sample produces characteristic X-rays that can identify elemental information. Samples must be vacuum compatible, so it may not be possible to process organic materials. So a big problem with some of the characterization tools in a vacuum, most biological systems contain water, and naturally that vacuum is going to want to draw that water out or dehydrate the sample, so that interaction isn't possible in a lot of tools. EDS can give quantitative results for samples that are flat and homogeneous. Relative X-ray intensity varies with the angle of the surface, so irregular surfaces can cause scattered X-rays. So these things have to be relatively flat on the atomic level. Analyzers are then used to characterize the X-ray photons for their energy or wavelength, and abundance determines the elemental makeup of the area under the test. So EDS can be used to gather pinpoint information or to map the elemental composition of a larger typical spot size of a larger area. A typical spot size, I guess there should be a period in here. Typical spot size is about 1 micron. The test is inexpensive and widely available on many SEM, TEM systems. And a lot of systems, what you can do if you have one at your facility, you can actually get a second vendor to provide like an EDS add-on to your tool. They can be used for a number of industries, aerospace, biomedical, biotechnology, electronics, pharmaceuticals, and the photonics industry. Now we'd like to take a look at X-ray photoelectron spectroscopy, and they call that one XPS. So XPS, X-ray photoelectron spectroscopy, is known as electron spectroscopy for chemical analysis, and that's called ESCA or ESCA. And I notice a lot of times our friends in chemistry or chemistry majors like to call XPS ESCA. It is used to determine quantitative atomic composition and chemistry. A sample is irradiated with monochromatic X-rays, resulting in the emission of photoelectrons whose energies are characteristic of the elements within the sample volume. An XPS spectra is created by plotting the number of electrons versus their binding energy. So this is similar to EDS that we just examined, except in this case what we do is we use X-rays as our initial signal, and what we're looking for is the X-ray interaction to actually emit photoelectrons. So this is a little bit different. It's exactly kind of like the opposite. Before we were using an EDS, we were using electrons to get X-rays, and right now we're using X-rays to get electrons. So this is a cartoon schematic of our system. So we have an X-ray source here, and typically X-ray sources are high energy metal interactions. So what we have is a culminator, which will help us focus our beam. And then what we do is we cast that onto our sample. We have our sample aligned so that that refraction of that X-rays is going to shoot electrons into our collection lens. Then from there what we do is we do a rastering of the electron energy to depict their actual energy on the surface. So an X-ray beam is usually comprised of K-alpha X-rays is focused on the sample. The absorption of incident X-rays results in the ejection of electrons. The energy of ejected electrons is measured by the detector. So here's a simple schematic on the right that shows what we're doing. Each atom has a unique XPS spectra. The spectra shows the binding energy of the electrons in the electron locations such as 2s, 2p1, 2p3, etc. XPS can be used to determine elemental composition, stoichiometry, the electrical chemical states, and examine the surface contamination. XPS is an elemental analysis technique that's unique in providing chemical state information of detected elements, such as distinguishing from sulfate and sulfide forms of the elemental sulfur. So that's certainly an advantage. So the range in materials for XPS, well, it requires ultra-high vacuum. So we have to have sample compatibility with ultra-high vacuum environment. Might be issues with biological samples, as it is in many cases. The sensitivity, it measures the elemental composition of the top 10 nanometers or so of the material. It can detect all elements except hydrogen and helium. Again, those are lost in a lot of characterization techniques typically. Detection limits typically are about 1/10 of an atomic percent, and typically the smallest analytical area is about 10 microns. Before we said in EDS it was about 1 micron. Material analysis, it can analyze metals, organics, and polymers, and the sample again has to be compatible with the ultra-high vacuum environment. So now we're going to move on to another test, which is a really test that gives a heck of a lot of resolution. SIMS. So it's secondary ion mass spectroscopy. SIMS is a destructive characterization method for determining the chemical composition of a material. So this can't be used in production. What you have to do is sacrifice the sample because it's a destructive test. The measurement can be done at the surface of a sample or utilizing simultaneous ion milling. The composition as a function of depth can be determined. So what we can do is when we initially shine our ion gun on the surface, we're looking at that surface. But as the ion gun interacts with the surface, it actually mills it away. So if we would keep the gun in the same spot, we can actually dig into the sample and get resolution as a function of depth. The measurement tells us what atoms are present, but it does not get information on the chemical bonding. And that was an advantage in the previous technique that we just examined, but it's not offered here in SIMS. SIMS is the most sensitive technique available for determining material composition. It can detect down to parts per billion. So that's a really big advantage with SIMS. So when somebody walks up to me and says, what do you think about SIMS as an engineer? I always think a lot of things that are on this front sheet, I think that it's destructive. And then I always think that it has a really high level of detection. So principles of operations. Ions are used to interrogate the sample. So ions are accelerated onto the sample. So we create ions, accelerate them and focus them at the sample. When they strike the sample, it emits secondary ions from the surface of the sample. The scattered ions are accelerated and positioned by a series of magnetic fields. The ions then go through a mass analyzer to separate ions for analysis. So what we're doing is we're using ions as our initial signal, and what we're trying to create is ions from the surface of the sample. So here's a block diagram of the system. So we see on the left-hand side here is our ion source. Then we have an attraction grid to pull the ions out of the gun. Then we have an analyzer magnet which selects the appropriate ion. That's like a filter. And then that hits the specimen. Then the specimen, what it's going to do is be able to emit ions. These ions are going to be collected with the extraction lenses. Then they're going to be placed through a magnetic analyzer. And then they're going to be put into a Faraday cup and then counted. So basically what we do to get these counts here, like on these masses, these individual masses, what we'll do is we'll adjust the magnetic field so we select the appropriate ion. When we select that appropriate ion, we filter that ion out that has the appropriate charge to mass ratio that can make it around the bend. Then what we'll do is we'll sit there for a few seconds or whatever the timing on the machine is, and we'll do a count at that point. Then what we'll do is we'll change the magnetic analyzer again to get our new reading, our new ion count. And then from what we're going to do there is we'll count those ions for the same amount of time. Then we'll move to the next magnetic analyzer, change the magnetic flux on the magnetic analyzer to select a different ion. So SIMS, the ion beam, can be moved quickly across the surface for near-surface chemical analysis, or the beam can be focused on one area, and that when it's focused in one area, what it's going to do is dig a profile into the sample. Typically, the beam spot is approximately 1 micron in diameter, and of course this can vary by tool. The ion source is typically CS plus, O2 plus, O, argon plus, Ga plus, and the energies run between 1 and 30 keV. And it's interesting to note what we try to do, and we'll look at in a little bit, is we have these different ion sources, and what we do is we select them. So when they hit into the sample, we do not confuse that initial signal with our output ions. So these are different ions that we ignore when we're looking at our sample. So we would use, there's a list that tells us what material is appropriate for what material that we're looking at. So the ion species will contaminate and interact with the surface depth of approximately 1 to 10 nanometers. And again, that information, the ions, the initial ions, the ion source, has to be removed from the reading. So there's 3 types of emitters basically in most systems. There's gaseous ionization by electron ionization. There's surface ionization of CS ions, and there's liquid metal ionization. So this shows the different types, and typically the beam currents that are associated with these different sources. And then these different sources actually have a beam focus capability in most machines. So we would estimate that the gaseous ionization has a rough beam focus, the surface ionization has a fine to rough focus, and the liquid metal ionization has the best beam focus at very fine. So gaseous ionization uses an electron gun to ionize gaseous source of elements or molecules. The ion beam created by this technique has a high current, but it's roughly focused. Surface ionization. In surface ionization, cesium is evaporated through a tungsten plug. This creates a cesium ions. This technique creates either a tightly focused ion beam or a high current beam. There's a trade-off there. For liquid metal ionization, a tungsten tip is covered in a metal or metal alloy that is typically liquid at or near room temperature. When a tip is subjected to high electric field, the tip will emit ions from the covering metal. This process is capable of producing very tightly focused ion beams of less than 50 nanometers. The electric field is used to create ions can be turned on and off in order to create pulsed ion beams. So some issues with SIMS, as we discussed before, the ion source is cesium or oxygen, argon, gallium at energies between 1 and 30 keV. These incoming ions can chemically interact with the substrate, so we try to select them so they don't. The beam chemistry is selected to minimize this reaction. Beam chemistry and energy selection are part of the art of this procedure. So here's the cesium and oxygen ion selection. And what we can see here is for these types of chemistries on this list, we would utilize oxygen for the least amount of interaction at the surface. And then for these primary ions that we were looking for, we would use cesium. So this is the color chart over here, the same thing. If we were looking at what we would be using oxygen for, that would be the guys that are here in the, I guess that would look green or gray on your monitor. And then the cesium primary, negative, and secondary emission are going to be listed here in that orange peach kind of color. So SIMS, again, the ion beam will sputter at an approximate rate of 0.5 to 5 nanometers per second. Naturally, the sputter rates are a function of the primary beam intensity, sample material, and crystal orientation. So that's an estimate, and you know, they're variable due to the interaction of the beam and the material. The sputtered substrate ions will be approximately 1% of the incident ion stream. So what we're looking for is the incident ion stream is going to be a very large signal, and the sputtered ions that come off are going to be relatively small. So that's why we'd like to filter them out. So note here in this drawing, the primary ion beam can contaminate the surface. So when the ions are coming in, now they become part of the surface because they get stuck in there. they can find their way into some area down in here and be ejected later on. The ejected species contain the incident ions, the sample material, electrons, and photons. The secondary particles carry negative, positive, and neutral charges, and they have kinetic energies that range from 0 to several hundred electron volts. So this is the detection that you see that the computer produces from our detector. The mass spectrum detects both atomic and molecular ions. The charge to mass ratio can be misinterpreted. Naturally, the molecules can be disassociated into atomic fragments. This is especially true of organic media. So what this shows is that different materials can break up into different forms, and you have to look at those primary forms and then the secondary forms of those materials. And what we can do is, if we were curious about one location, we can actually take our screen, and zero it here and get more resolution in between that area in the software. So here's an interesting SIMS analysis of a drug. So what they're showing is they look at the drug and see how this drug is actually displaced throughout the matrix that carries that drug. So often drugs might be a small amount of the pill that you take. There might be other buffers or release agents in there, or sugar or something like that. So they try to get a mixture in there. And so what this does is shows you the analysis of a drug that you're trying to sell to the public. So some SIMS issue. So secondary ion signal from the sample might be shielded from reaching the detector due to substrate charging. So that's a big issue. So when we're ejecting those ions, naturally we're losing charge from the surface. So dielectric samples might charge negatively and prevent positive ions from reaching the detector. So those would actually act as an area for those ions to go to. There are a few ways of preventing this negative charge buildup. High energy electron beams are used to add negative charge to the sample. This E-beam might interfere with the quadrupole detector, so you have to be cautious of that or factor that out of the measurement. Dielectric samples can be coated with a conductive layer, but naturally this layer will be included in the analysis, so then that will have to be removed from your analysis, that conductive layer. Software can add an offset voltage to compensate for negative charging. This is not a total solution, but more of an aid. So as you do the measurement, the system will shift, and you can take care of the shift through the software. So looking at, again, some SIMS issues, atoms from the sample's outermost monolayer can be driven in about 10 nanometers. This type of damage is called surface mixing or knock-on. This creates a surface roughness lattice imperfections. And we can see here the primary ions come in at 10 keV. We get this mixture where it goes throughout the sample, etc. And then we see the secondary ions, atoms, and molecules coming off the surface right here. So we're looking at sputtering also creates surface roughness and lattice imperfection. And naturally, as I said in the first slide, one of the first things I think about when SIMS is a destructive test. So if we were looking at this, the primary ions coming in to hit in this area, if we would leave this beam in this area for a long time, we would just start continuously digging a trench through the sample, and we would be able to get more information as we sputter down through the sample. So this is our initial sampling depth, but we can go down about this far. Now we're going to move on to our final characterization tool that we're going to examine today. It's Fourier transform infrared spectroscopy. And again, what this stands for, what we're going to do is this technique measures the infrared light absorbed by a sample. Fourier math principle is used to correlate the absorbed band of light from the incident infrared to a specific bond. This technique is based on the principle that bonding between atoms is like a spring. These bonds vibrate at frequencies that match those of the infrared light. Therefore, a specific portion of the infrared light spectrum can excite these unique bonds. Simply stated, different bonds vibrate at different frequencies and will absorb only radiation that matches that specific frequency. This absorption can therefore be used to identify bonds using IR radiation. This method is used to detect and identify molecules present on a surface or detect and identify the chemical bonding in a thin film in a non-destructive manner. So this test is non-destructive compared to SIMS. This method simultaneously collects data from a wide spectrum range. Basically, infrared light is split in between two beams. These beams interact with a moving mirror to produce an interferogram. This is the part of the interferogram is absorbed by the sample, and this waveform is indicative of certain bonds. So FTIR can be used to confirm the identity of pure compound by seeing bonds types present. It can detect the presence of specific impurities by seeing bonding, detection of biological entities by seeing bonding, detection of bonding and therefore chemical composition of thin films, and it can be used as a non-destructive characterization tool in production. So this is a schematic drawing of an FTIR system. The beam splitters transmit half the beam to a moving mirror and half to a fixed mirror. They reflect and then recombine in a comparator. The mirror moves to recombine the beams constructively or destructively. So what we have is our infrared source. We take that infrared source and we break it up into two systems. And in one of the systems, what we're doing is we have a moving mirror, and then we actually add that to a non-moving mirror. So we take half the light from the infrared and we take it to a mirror, and that is non-moving, and then the other half is moving. When we take those two and recombine them, what we do is we get this interferogram signal. So the detector reads the beam as a continuous electrical signal called an interferogram. The computer converts the interferogram into a graph. So now we take this signal, represented by this, take it through our sample, and what it does is that sample is going to absorb some of these waves, these rich parts of these waves, and then what the Fourier math does is it transforms that signal into actually the chemical bonds right here. So what we do is we go from this area here where we're talking about light we transform that into talking about bonds, and the magic here is to use Fourier math. So the electrical engineers are all in on Fourier transforms, etc., and convolution, and that's what this topic has to deal with. But simply what we're doing is we create a signal in this area with these mirrors, and this signal is going to be rich in certain bonds. So as we move the mirrors, what we're doing is we're discovering bonds or interactions of that light within the bonds of the material. So this interferogram is going to change as the mirror moves, and what we're going to do is we're going to be able to actually look at specific bonds. As we move that mirror, we go from this resolution, talking about that identity, and then we move into the bond identity. So absorbance and transmission, excitation energy is taken out of the infrared light and converted into mechanical motion. The infrared light that isn't absorbed by the sample gets reflected or transmitted. This non-ideal loss must be quantified. Energy that's transmitted and reflected must not be confused with energy that's absorbed by the sample. Energy absorbed by the sample holder and other variables are collected from a reference trial. This reference data is subtracted from the actual test, so the sample data is free from artifacts. It's also important to purge the chamber with nitrogen to eliminate water vapor and carbon dioxide that could absorb the infrared signal. So what we have to do is generally when they do a FTIR run, it's very typical you would place a blank sample holder in the system, purge the system with nitrogen for a while, and what that nitrogen is going to do is it's going to, from the chamber area where you put the sample in, it's going to eliminate the water vapor and carbon dioxide. So then you'd be in a steady state without those gases in there to absorb the signal. And then what you'll do is take a measurement, and you're going to measure the sample holder. So the sample holder itself is going to absorb some of the infrared, and what you're going to do is save that data, place your sample in, do the same procedure where you're going to eliminate carbon dioxide and water by putting a nitrogen purge in the system. Typically that's 10 or 15 minutes. And then what you're going to do is measure your sample on the sample holder, and then at that point the computer is going to subtract the previously saved data of the sample holder, and then you're going to know what was been absorbed by only the signal. So what we're trying to do in this point is look at what's been transmitted through the sample and what's been absorbed by the sample. And what we want to do is eliminate absorbance from the sample holder and from water vapor and carbon dioxide. So this just shows a cartoon here that shows us the different forms of water and how this water is going to absorb the infrared light. And these are saved in a computer, and you can compare them to your sample in a library. And this is a FTIR spectra of alcohol. And what we can look here is to see this typical absorbance on here. So these libraries are available online. You could also purchase libraries that have different chemicals and different known materials in them, so that you can actually get your data and then search the computer and see a good fit for your product. So the FTIR detects the identity of a pure compound by seeing bonding types present. FTIR also detects the presence of specific impurities by seeing bonding, detection of biological entities by seeing the bonding, and the detection of bonding and therefore chemical composition of thin films. Again, this is a non-destructive characterization tool. And as I said before, the FTIR tool can have a library of spectra that can be compared to known samples. This library can be used to verify quality or consistency control in the manufacturing, or the library can be used for investigative work.